Okay. Last part, right? Compacting of iodine molecules in solid state, right? Okay. It's yeah. I think it would be better if you cut iodine. Cut off that iodine. Okay. Compacting of molecules in solid state, right? Right. Okay. Let's take iodine as an example. Iodine is a iodine exists as a what? Which lattice? Molecular lattice. Yeah. Especially polar molecular lattice or non-polar molecular lattice. Non-polar molecular lattice, right? Iodine exists as non-polar molecular lattice. Okay. So arrangement of I2 molecule, right? Arrangement of I2 molecules in solid state will be like this. Right? Okay. See whether it follows in order or not. Yeah. Okay. There's an order, right? Like this. 1, 2. Like this. Right? Right? Okay. You can see that, right? I2 is a molecular lattice. Polar molecular lattice or non-polar molecular lattice? Non-polar molecular lattice. So that's why it's normally insoluble or less soluble in water, but highly soluble in organic solvent. Normally organic solvents are non-polar, right? There's a law like dissolve like dissolve like. That means polar compounds are soluble in polar solvent. Non-polar are soluble in non-polar solvent. Okay, iodine is a non-polar, so it's soluble in non-polar solvents, right? Okay, not only chlorine, not only iodine, also bromine, chlorine, yeah, all dissolve highly in non-polar solvent, right, or organic solvent, right? But less polar, less soluble in water. Water solubility is very low for this. But polar compounds like ammonia, those compounds highly soluble in water, right? Because they are polar. They dissolve in polar solvent like water, right? Okay. Water I2. Which compound has a large boiling point? Okay. Boiling point and melting point depends on, but it's very important point. This is very last part and it's very important part, right? Okay. You need this in organic chemistry also, right? Okay. So which one has a higher boiling point, you think? Which compound has a higher boiling point? Water or I2? What? I2. Why? In I2. What? Between I2 molecule, what kind of interactions are there? Only London dispersion force. Why? It's a non-polar molecule. Between water molecule, what? Yeah, there will be London dispersion force. Additionally, dipole, not normal dipole, hydrogen bond, right? Hydrogen bond. So only London dispersion force plus hydrogen bond. So boiling point will be higher for water, right? Okay. What's the boiling point of water? 100 degrees. I do. Okay. I don't know the exact value, but I think 180 degrees something. Very much large. Okay. I have already mentioned that London dispersion force depends on molecular size. Right? Now, I'll draw the H2O. This is H2O. Oxygen and 2 hydrogen. Right? Let's draw iodine. Only single atom, only just a single atom is very much larger than this, right? You know, oxygen. In periodic table, what's the atom? What's the element next to oxygen? Fluorine, right? Oxygen, and if this is oxygen, fluorine, little bit smaller than this, almost equal size. Fluorine, almost equal. This is oxygen, fluorine, almost equal. What about chlorine? Very much larger than fluorine. Bromine, even larger. Iodine, very much larger, right? Okay, same group, fluorine, bromine, iodine, right? Okay, single iodine atom will be like this. But there is another one too. Okay, so between I2 molecule only London dispersion force here. London dispersion force here. London dispersion force plus dipole moment. But only this London dispersion force is greater than that of strength of this London dispersion force will be greater than that of the sum of these two. Okay, there are two forces, but very much large. Why? London dispersion force is very small, very weak here, but here it's very strong. It's strong, as larger than the sum of these two. Okay. Okay, so don't just compare by the dipole, polar or non-polar. Polar compounds are always higher boiling than non-polar. No, it's wrong. It depends on size or molecular mass also. Both are same. You can take size or molecular mass, anything, molecular weight or size. Right? Okay. First, see the molecular weight. If the molecular weight is very much larger than this, then it would have the higher boiling, because London dispersion force will be very much larger. If the molecular weights are comparable, like there are two molecules, two substances A and B. Molecular weight of A 40, molecular weight of B 42, almost equal size. So London dispersion force will be almost equal. Say A is polar, B is non-polar. So which one have higher boiling point? A. Why? London dispersion force for both molecules, London dispersion force are same. Additionally, A has dipole attraction. So total attraction is very much higher for A. So A will be higher boiling. Right? Okay, got it? So if you want to compare boiling point by interaction, by intermolecular interaction, first you should see the molecular weight, and then only you should see what? Whether the molecule is polar or non-polar. Here, molecular weight, water, molecular weight is, I think, hydrogen 218. Even one iodine, I think 127, so 254. Okay, so this has the 2 times even 1.5 time, yeah, the high the large molecule will be higher boiling. But 2 times around, so this is molecular weight of this is 80, 160. So it should be higher boiling, right? Remember that. But it should be even 1.5 time. Yeah, that should be high boiling. If it's comparable or almost equal only, you should compare the boiling point by polarity, right? Okay. See this chart. Okay. In this chart, compare first to O2 and NO. What is the molecular weight or molar mass? 30 to 30. Is it comparable or not? Yeah, comparable. That means almost equal. So what so to compare boiling point, what you should see? What you should look for? Polarity. See? O2 is an unpolar molecule. That, see, dipole moment is 0. NO, dipole moment is 0.153. Just determine whether is the molecule, whether the molecule is polar or not. So NO is polar. So what is the boiling point? See the boiling point. O2 minus 183, NO minus 152. Okay. So which one is higher boiling? NO. Why? It's polar molecule. Better? Okay. And krypton, it's a monoatomic molecule, but the molecular weight is 83. So now compare NO and krypton, second and third. 30, 83. What about the boiling point? Equal. Why? What's your expectation? Which one should be higher? Second one, NO. Why? It's polar, Kr is non-polar. Monoatomics are non-polar, but boiling points are almost equal. Why? Yeah, third one, krypton is non-polar, but it's very much larger in size. Oh, very much larger in molecular weight. Weight of the bond, right? And now krypton and HBr. See, what about the molecular weight? Almost same or not? Yeah, molecular weight is almost same. So London dispersion force. What? Same. Better? London dispersion force is equally strong. But you know HBr is a polar molecule. So additionally, dipole attractions will be there. So which one is high boiling? HBr. Okay, you see that? Yeah. Minus 152, HBr minus 62. And HBr and Br2. Compare that HBr and Br2. Molecular weight 81. HBr molecular weight 81. Br2 160. Twice. Yeah, almost twice. So which one would be high boiling? HBr or Br2? HBr is polar, Br2 is non-polar. But which one is high boiling? Br2. Why? Molecular weight is very large. Molecular weight is very large. So 59, right? And what about last two? Br2 and ICl. Both are almost same in molecular weight, right? Sizes are same. Br2 160 and ICl 162.5, almost same. So if the size is same, what you should see? Polarity. You know Br2 is non-polar and ICl is polar. So what? Yeah. Boiling point of ICl will be higher, 97. Okay. Okay, you should fill the last column. Type of dominant interaction, right? O2, what's the dominant interaction? O2, London dispersion force. In NO, there are two forces. In London dispersion force, dipole. What's the dominant? Dipole. KR, London. HPR, dipole interaction. BR2, London. ICL, dipole interaction. Quickly note it down. Almost like that. Okay. What? Okay. What's the molecular weight of this? C5 molecular formula C5H12. Okay. What's the molecular formula of that? Same. C5H12. Same. Right? So what about the boiling point? What about this is N-pentane, that is neopentane, right? So what can you say about the boiling point? Yeah, equal, because both are non-polar molecule. Both are normally hydrocarbons are always non-polar. Keep it in mind. Hydrocarbon means what? Compounds contain only carbon and hydrogen. Always, normally hydrocarbons are non-polar. So between hydrocarbon molecule, what? Only London dispersion force. Right? Strength of London dispersion force should be equal. You think why? Size is equal. Molecular weight is equal. Right? Boiling point of this one is yeah, 36 degrees C, and this one is just 9 degrees C. boiling point. So you can say this one is liquid at room temperature. Normally what's your room temperature? 25 degrees C. So this one is liquid, isn't it? Why? Your room temperature is 25. Boiling point of this is 36. So in room temperature, at room temperature this will exist as a liquid. And what about this one? It exists as at room temperature. This one will be a liquid or gas. Just think and tell. Gas. Why? The room temperature 25. Its boiling point is less than that, 9. 9 full boil air. So more than 9 degrees C, it exists as a gas. Right? Exists as a gas. Right? So it's a gas and it's a liquid. Right? Boiling point is different. Right? This is why it has higher boiling and it's low boiling. Why it's higher boiling and that one is low boiling. Why? Okay, let's see the shape of that. Right? This one is almost a spherical in shape. Right? Spherical shape, and this one is linear shape, chain shape. Right? So these CC bonds are more exposed here. Right? CC bonds are more exposed, but here CC bonds are shielded by these groups. Right? So you can see that CC bonds are well shielded there. So the attraction, London dispersion force between two of these molecules will be strong because the bonds are CC bonds are exposed or less, right? Highly compact. Right? Okay. Okay. Got it? Yeah. Last page. Last page. Last paragraph. Last paragraph. Fourth line. Fourth line. Last paragraph. Fourth line. Half line. Hence, the London forces in N-pentane are, this is N-pentane and this one is neopentane. London forces in N-pentane are stronger than those of in neopentane. This is because the spherical shape of neopentane molecule and the valence electrons in CC bonds are well shielded from the CH3 groups, whereas N-pentane is chain shaped so that valence electrons in CC bonds are more exposed in order to form London dispersion. Okay. So if any molecules want to form London dispersion force, what should happen? What's the requirement? All valence electrons should be close together. Or valence electrons of this molecule and valence electrons of other close molecule should be close enough. Right? Okay. So what about here? There's another C. Hydrogen electrons okay, carbon this carbon bonds and this carbon electron little bit distance, but there the distance is very much larger. Okay, very much larger distances, right? Okay, so the London dispersion force is very much weak. right? So linear molecule, linear structure, straight line molecule or linear molecule or chain molecule. Chain molecules has higher boiling point compared to the branched one, right? Okay. Understand? Okay. Yeah, that's all. Okay, second unit got to easy. First unit so first unit periodic properties I